All right, so today we're gonna wrap up the floating point specification, IEEE 754 floating point specification, which is how our computer represents, real numbers on the computer. But of course, they're not actual real numbers. They are approximations of real numbers, right? And so we have 64 bits in double precision, which is what our computers use and R uses, and most programming is done using double precision floating point numbers. And we talked about this on Monday, and we're going to wrap this up today. And anyway, we got 1 bit for the sine, 11 bits for the exponent, 52 bits for the mantissa. So that makes your 64 bits. Okay, and to kind of illustrate the system, we're going to use a mini float. Okay, and we're going to see kind of similar things happen with the mini float, but and you can just imagine this applying to the double precision. Okay, so for the mini float, we've got 1 bit for the sine, 3 bits for the exponent, and 4 bits for the mantissa. Okay. Okay, the first bit's the sine bit, 0 for positive, 1 for negative. 3 bits for the exponent. Okay, with with 3 binary digits, you can represent 2 to the third or 8 unique values. Okay, you can represent 8 unique values. We want half of these to be positive and half to be negative. Okay, and so we're going to introduce a bias. Now, the engineering specification, engineers chose to do, rather than 8 divided by 2, 4, they do 1 less than that. So the way you can figure out your bias is you say, okay, well, 2 to the third is 8. Half of that is 4. Okay, so that's 2 to the n minus 1. Okay, so half of that is 4, and then 1 less than 4 is 3. So our bias is 3. Okay, so if you have all zeros, then it becomes negative 3. 0, 0, 1, which is 1 minus 3 is negative 2. 1, 1, 0 is 6, minus 3 is 3, okay? So we have a bias of 3. When you have 11 bits in the exponent, okay, 2 to the 11 is 2048. Half of that is 1024, okay? And 1 less than 1024 is 1023. So your bias with 11 bits is 1023, okay? If you had 4 bits in the exponent, what would your bias be? 4 bits in the exponent. All right, somebody's got to know, right? 7, right? So 2 to the 4 is 16. Half of that is 8. 1 less than 8 is 7, okay? And that's how we figure out the exponent bias. We basically want half to be positive and half to be negative, but we're going to do 1 less than that so that there's an extra positive number and one less negative number, okay? All right, and then the last 4 bits are for the mantissa, okay? Because we're always going to assume that the numbers are in normalized binary scientific notation. Normalized means your leading digit cannot be 0. Okay, so in normalized binary scientific, the leading digit will always be a 1. If it's not a 0, it has to be a 1. That's binary. Okay, and so you've got the 4 bits will be 4 bits after the leading 1. Okay, all right, so try this out, okay? Maybe take out a piece of paper and tell me what this number represents. 10, 10, 10, 10. What is that in binary? You got 3 bits for the exponent, 4 bits for the mantissa. The leading one is a well, I guess maybe it'll take too long. I don't know. Maybe you guys will get it, okay? But let's just start with the exponent. What are the exponent bits, and what exponent value does that represent? Okay, so the exponent bits are 0, 1, 0. It's the next 3. The first one's the sine, and then the next 3 are the exponents. So we have 0, 1, 0. What is 0, 1, 0 in binary? 0, 1, 0 in binary is 2. What's the bias? 3. The bias is 3. So 2 in binary becomes, or the exponent becomes -1. Okay, the exponent becomes -1. So the exponent is 0, 1, 0, which is 2. The bias is 3, so the exponent is -1. Okay, so the mantissa bits are 1, 0, 1, 0. And with the leading one, that's going to become 1.1010, which is going to be 1 plus 1/2, no fourths, plus 1/8, and no 16ths. So I've got 1 plus 1/2 plus 1/8 multiplied by 2 to the -1. All right, so this adds up to 13/8. There's a negative sign, so 13/8 times 1/2. This becomes -13/16. Is that all right? So the 1 here is a 1. Right behind the binary point is a 1/2. The next spot over is a 1/4, but that's a 0. And the next spot over is an 1/8. And there's one of those. So we're going to do 1 plus 1/2 plus 1/8. Is that good? All right, another option is you could take this, and because it's in binary scientific, you can kind of roll that binary point. You can move it over to the left or to the right, depending on whether it being positive or negative. So in this case, it's negative, so I would roll it one spot over to the left, to the -1. I move it one spot to the left, and I get 0.11010, which becomes 1/2 plus 1/4, no 8ths, and 1/16, and that also adds up to -13/16. All right, okay, so we run into a problem though, right? So here I've got 0, 0, 0, 0, 0, 0, 0, 0. Okay, I've got 8 binary zeros, right? Intuitively, we feel like this should represent 0, okay? But with our current system, this doesn't represent 0, right? Because what happens, so we get the bias, the exponent is, the exponent bits are 0, 0, 0, which is 0 minus 3, we get -3, 2 to the -3. But the mantissa bits, we're always assuming is led by a 1. Okay, so we're going to have 1.0000, right? So I've got 1 times 2 to the -3rd, that's going to be 1/8, right? And we like the idea, we like having a leading 1 that reduces redundancy, but if there's always a leading 1, there's no way to represent 0. Okay, there's no way to represent 0 if we're always assuming the mantissa has a leading 1. Okay, so we have something called denormalized mode. Okay, in denormalized mode, when the exponent is all 0, if the exponent bits are all 0, then the leading digit in front of the mantissa bits becomes a 0 as well. Okay, so this is the key. Okay, when the exponent bits are all 0, the digit in front of the mantissa bits is 0. Okay, and then to prevent a discontinuity in the numbers, okay, the exponent bias is going to be 1 less than normal. So for a mini float, our exponent bias is normally 3, but in denormalized mode, our exponent bias is 1 less than normal, so we have 2. In the double precision, our exponent bias is 1023, but in denormalized mode, it's 1 less than normal. It's going to be 1022. Right? And so I'll illustrate all of this here. Okay. So if we have all zeros, then the exponent bits are all zeros, and this puts us in denormalized mode. Our bias is 1 less than normal, which will be 2. And with a bias of 2, the exponent's -2. The mantissa bits are all 0, and the leading digits is 0. So we got 0.0000 times 2 to the -2, which is still 0. Okay? And so having all 0 will represent the number 0. Okay? So this is the IEEE 754 specification. If you have all 0 bits, that represents the number 0. Okay? And that makes intuitive sense to us, I think. Okay? And then we also have 2 other special cases for the exponent. Okay? If the exponent is all 1s, then it's either going to be infinity or not a number. Okay? So if the sign bit is 0, you got positive infinity. With 1, you got negative infinity. Okay? Exponent bits all 1. If the mantissa bits are all 0, that's infinity. Okay? For not a number, Okay, exponent bits are all 1, and you have anything other than all 0. Okay, so there's lots of combinations or lots of ways to represent not a number. Any combination of bits not all 0 will be not a number. Okay, and so the other thing is that not a number, nan, is always a type double. Okay, or a type, a floating point number. There's no integer representation for not a number. We don't have that. So for nan, there's not an integer representation. It's always going to be kind of a floating point thing. Right? And this is going to be the case for any other languages as well. So if you're dealing with, say, Python, and you want to represent missing values, you can't do it with integers. Missing values with nans. So Python doesn't have a missing value. They only have nans. Okay. In R, we have nan, and we also have missing value, na. And those are actually just different things. Okay. Python doesn't have na. You've got nans, and that's how you represent missing values. Okay, but it's going to be a floating type. You can't have missing booleans or missing other things. All right, so let's kind of look at this. This is the smallest non-zero value we can represent. 0 for the sign, 0, 0, 0 for the exponent, and 0, 0, 0, 1 for the mantissa. Can you guys figure out what this value is? Okay, so I'll help you out a little bit. Okay. Exponent bits are 0, 0, 0. Our bias is 1 less than normal, so we have a bias of 2. So this is going to represent negative 2. Our exponent is negative 2. The mantissa bits are 0, 0, 0, 1. We got 3 zeros and a 1. And in denormalized mode, we're in denormalized mode because the exponents are all 0. The leading digit is 0. So I've got 0.0001. 0.0001 times 2 to the negative 2. Okay? So what is 0.0001? What is that? 1/16th, right? 0.0001 is 1/16th times 2 to the negative 2. 2 to the negative 2 is 1/4. So 1/16th times 1/4 is 1/64th. Okay, so the smallest non-zero value we can represent with our mini float system is going to be 1/64th. Okay, what would be the second smallest value we can represent? Okay, so this is the smallest one. The second smallest one will be this, right? So I just kind of add 1 to the, and I get 1, 0, so I got 2 of these. Okay, so 1/0010 is 1/8. 1/8 times 1/4 is 1/32 or 2/64. So we've incremented from 1/64 to 2/64. Okay, and we can keep counting, and this would be 3/64, 4/64, 5/64, 6/64. Okay. What would be the largest denormalized value I can represent? All right, so I have 4 bits for the mantissa. 4 mantissa bits. What would be the largest number I can represent? Denormalized. So meaning my exponent is 0, 0, 0. My exponent bits are 0, 0, 0, and I'm going to have, I've got 4 mantissa bits. What's the largest number I can represent with 4 binary digits? What's that? 1, 1, 1, 1, which is equal to 1, 1, 1, 1 would be what? 15. 1, 1, 1, 1 is 15, right? Okay. So the largest number you can represent with 4 digits is basically 2 to the 4 minus 1, because 2 to the 4 you can represent 16 unique values, but one of those values is 0. Okay, so it's going to go from 0 to 15, right? So if you think of, if you got 10 unique value, 10 binary digits, what can you represent? 2 to the 10 is 1024, okay? And 1024 minus 1 is 1023. So you can go from 0 to 1023. That's the biggest number you can represent with 10 binary digits, okay? So you should know your powers of 2, right? So 2 to the 8 is 256. Okay, so you go from 0 to 255, and then 2 to the 10 is easy because 2 to the 10 is approximately 1,000, and it's going to be 1024. So okay, so this is the largest value, denormalized value we can represent. Basically, 0, 0, 0 for the exponent and 1, 1, 1, 1 for the mantissa, and that's going to become 15/64. Okay, the 1, 1, 1, 1 is 1/2, 1/4, 1/8, 1/16. That's 15/16 times 2 to the negative 2 because we're in denormalized mode. This becomes 15/64. What would the next value be? The next, if I add 1 bit to this, what would the next value be? Well, what would the bits look like? So it looks like we're just counting in binary, right? So this is so one thing about binary is like, can you imagine like the odometer in your car rolling? Like you got like 9999, and then if you add 1 to that, what happens? It becomes like 10,000, right? So if you got 9,999 miles and you add one more, you get 10,000, right? And it's kind of like that, except it's you only have 2 digits, 0 and 1. So if I add 1, then it becomes this, right? So this is the biggest. With 4 digits, I go 1, 1, 1, 1. That's like the equivalent of filling out 9999, and then I add 1, and then it becomes 1, 0, 0, 0, 0, right? So it's like 10,000 here, okay? And what does this represent? Okay, so now we are in normalized, right? So this is the smallest normalized value I can represent. The exponent bits are 0, 0, 1, okay? And so this is the smallest exponent I can have that's normalized. And so the bias is going to be normal, which will be 3, okay? Our exponent bias is 3. Yeah?
Why is the exponent bias normally 3?
The exponent bias is normally 3 because we've got 3 bits for the exponent. 2 to the 3 is 8. Okay, we want half of those to be negative. So half of 8 is 4. Okay, but just so that we have more positive than negatives, we're going to bias it by 1 less than 4. So the process is 2 to the 3 is 8. Half of that is 4. 1 less than 4 is 3. Okay, I know it feels convoluted, but it'll make sense. Okay, so if you have 5 bits, 2 to the 5 is 32. Half of that is 16. 1 less than 16 is 15. You would have a bias of 15 with 5 bits, okay? So with 3 bits, our bias is 3, okay? And that's our normal bias of 3. And so with the exponent being 1, 1 minus 3 is negative 2, okay? The mantissa bits are all 0, so we have 1 times 2 to the negative 2, which is equal to 1/4. And 1/4 is equal to 16/64. Okay, and the increment here is still 1/64, okay? The next smallest value, I would add 1 here, and this would become 1.0001, okay? Our bias is still 3, my exponent is still negative 2. I have 1 plus 1/16, or 17/16 times 1/4 becomes 17/64. Okay? And so if I keep doing this, then we're just counting. This is 18/64, 19/64, 20/64, 21, 22/64, okay? And this is actually, right now, if I said what is 18 in binary, it would be this, 10010. That's 18 in binary. This is 16 and 2 is 18. This is 19 in binary, 10011. 16, 2, and 1, okay? And so basically we're just counting by 64ths here, okay? Every time I add 1, I'm adding a 64th, okay? So what would the largest value be that I can represent while my exponent is 001? The largest value I can have with my exponent being 001 would be what? Basically, it would be 1, and then these would be all 1s, right? And that's going to be 31/64. Okay, I've got 1 plus 15/16, which is 31/16 times 1/4, because we're still at 2 to the negative 2, 31/64. Okay, so we're at 0001111. Okay, what is the next value going to be? If I add 1 to this, what will it advance to? Okay, again, it's just like the odometer, okay? So it's going to become 0, 0, and then 1, 0, 0, 0, 0, 0. So it's like reaching 100,000 miles on the car, okay? So it goes from here, and then the next value, if I add a bit, becomes this, okay? And this becomes, what does it become? It becomes 1/2, right? So here we're at 31/64. We're just shy of 1/2. I add 1, and now I'm at 1/2, okay? The exponent bits are 0, 1, 0, which is 2. Our bias is 3, as normal. And the exponent is 2 minus 3, negative 1. Okay? The mantissa bits are 0, 0, 0, 0. The leading digit is 1. So I've got 1 times 2 to the negative 1, which is 1/2. Okay? 1/2 is equal to 32/64. So I've basically just incremented to a 60 by 1/64 here. Okay? All right. So here's a question. What happens if I add 1 bit? If I add a 1 to this bit? I would have 0, 0, 1, 0, 0, 0, 0, 1. Okay? But what number is that going to represent? Okay? So far we've just been counting by 64ths, okay? And so we might say, okay, well here's, this number represents 32. 1, 0, 0, 0, 0, 0 represents 32. And you might think that the next number would be 33, and we should get 33/64 or something, okay? But here's the genius of floating point representation, okay? Because if everything represented 1/64, the largest number I could possibly represent would be, this thing becoming a 1, and so that would be, 64/64, and then everything fills out, and how I'd have like 1 and 63/64, right? That would be kind of the largest value, because as soon as this hits a 1, then we're at like negative numbers and stuff, okay? So I can only count up to like basically 2, all right? If every increment was 1/64, okay? So what happens is instead of reaching 33/64, we change our increment from 1/64 to 1/32, okay? So our step size doubles. Our step size is no longer 1/64, our step size is a 32nd, okay? And this is done via the binary scientific, okay? So our exponent is 0, 1, 0, which represents 2. The exponent is 2 minus 3, negative 1, okay? The mantissa bits are 0, 0, 0, 1. The leading digit is 1, so this is 1 plus 1/16. I multiply that by 1/2. 17/16 of 1/2 is 17/32, or 34/64. So rather than going from 32/64 to 33/64, we have jumped up to 34/64. My increment has gone up to be 1/32. Okay, and so now every time I increment this, and I go from 0, 0, 1, the next one, will end with 1, 0. This is 18/32. Okay, so we've gone from 17/32 now to 18/32. Okay, and we can kind of list all of these off, and this is 19/32, 20/32, 21/32, 22/32. Okay, so if I fill all of these out, the mantissa bits with all 1s, what will that be? So the mantissa bits with all 1s is going to be 31/32. Okay, so this is what I have. Okay, so I'm at 1, 0, 1, 1, 1, 1, 1, and that's 31/32. Okay, and if I add 1 to this, we would get 0, 0, 0, 1, 1, and then all zeros. And what will that number represent? So what's the next number after this? If I add 1/32 to this, I would get 1, okay? I would get 32/32 or 1. So this is 0, 0, 1, 1. My exponent is 0, 1, 1, which is exponent bits are 3. Okay, with a bias of 3, the exponent is 0. 2 to the 0 is 1. My mantissa is all zeros, so this becomes 1.0000, or 0.0000, yep. Times 1, that's 1. That's 32/32, okay? What is the next value? If I add 1 bit to this, what will that become? If I add 1 bit to this, I will get 1 and 1/16. There we go. All right. So each bit, right? We have 0.0001. So my mantissa with the leading one is 1.0001. That represents 1 and 1/16. My exponent is still 0. 2 to the 0 is 1. So this becomes 1 and 1/16, and this is 17/16. So my increment is no longer 30 seconds, but my increments are now 16ths. Okay? And so this continues on. I've got 16/16, 17/16. So I just keep adding 1 to these, 17, 18, 19/16. And then this would keep going until we reach here, 31/16, just shy of 2. All right? And if I add 1 to this, what will I get? So this is going to roll over, right? This is like reaching like 99,000 or 999,000 miles on your odometer. And you get 1 more, and this becomes 1 and then 0, 0, 0, and that's going to be 2. Okay? But now the increments are now 8s. Okay? So every time I add 1, we're incrementing by 8. We go from 16/8, 17/8, 18/8, 19/8, all the way up to 31/8. Okay? 31/8 plus 1 more 8 will give us 32/8 or 4, and that's going to be the next case. So we're going to be at 16/4, 17. So now our increment is double that. Okay? So we started off with increments of 64, and we're climbing up 64th at a time, and then we reach a point, and our increments become 30 seconds, twice that size. And then we reach a point, and once all of our mantissa bits fill out, the next increment becomes twice that, so 16ths. Once our mantissa bits fill out, the next increments becomes 8ths. Once those fill out, our next increments becomes quarters. And once these fill out, our next increment becomes halves. Okay, so I get 16 halves, 17, 18, and I get up to 31 halves. Okay, this is the largest number I can have before the computer says it's infinity, right? So it's a little silly. The biggest number it can represent is 15.5, which seems ridiculously small. But on our mini floating point system, this is the largest number it can represent, 15.5. After that, then all of our exponent bits become 1. Okay, and when all of our exponent bits become 1, and we have all zeros, this becomes infinity. All right, and that's just the specification. Okay, when it's all 1s here and all zeros, that's infinity. Okay, and if I put anything other than all zeros here, it becomes not a number. Okay, and that's just the IEEE 754 specification. You might say like, well, I could come up with a better system, but this is a good system, and we've used it for 30-something years. The engineers really did think a lot of things through, and so you'd be challenged to beat it. Okay, so all 1s represent and all zeros represent positive infinity. And this is the biggest number we can have that's not infinity, okay? And that's going to be 15.5. Okay, but the important thing to note is that the values close to 0 have tiny increments, and as we move farther away from 0, the increments double in size each time. Okay, so there's just a few things. Okay. Let's talk about double precision, right? I've got to add a few more slides here, and I'll do that later. But okay, the smallest positive non-zero value we can possibly represent is going to be sign bit 0. Exponent will be all 0 bits. Okay, that will put us in denormalized mode. And so our bias is normally 1023, but we're 1 less than normal, so that's negative 1022. And we've got 51 0 bits followed by a 1 bit. Okay, so I got 51 zeros and then a 1 here, so I've got 52 bits behind the mantissa. That's 2 to the negative 52. And so this is equivalent to 2 to the negative 1074. Okay, and I can ask for 2 to the negative 1074, whoops, negative 1074. All right, this is the smallest possible number I can represent on the computer. Anything smaller than this, if I ask 2 to the negative 1074, 2 to the negative 1075, the computer will call this 0. It is not able to distinguish it from 0. This is the smallest possible number I can get. Okay, I think I've done options digits equals like 17 or something like that. Oops, digits equals 17. Okay. So that's what we have. Okay, the smallest normalized value will be 10 0 bits followed by a 1 in the exponent. Okay, we got 11 exponent bits, so it's all zeros but a 1. So the bias is 1023. That gives us an exponent of negative 1022. The mantissa will just be all 0, 52 0 bits. Okay, so this is equivalent to 1 times 10 to the negative 22. Times 2 to the negative 1022. Okay, this is the smallest normalized value we can have. This is known as machine double X min, if I can spell. Okay, this is the smallest value I can represent. Okay, and if you type in dot machine, these are just values that it will tell you the biggest value can represent, the smallest value you can represent and stuff. Okay, so double X min is the smallest normalized value, and that's 2.225 times 10 to the negative 308. Okay, basically 2 to the negative 1022. Okay, double X max, double.x max is this number. Okay, and I haven't made a slide for this, but this is basically your exponent is going to be all ones but a 0. Okay, all ones but a 0, so that's going to be 1023, 2 to the 1023 times, and then everything, all the mantissa bits are filled out by 1. Okay, if you try to do 2 to the 1024, it says infinity. Okay, but 2 to the 1023 is it can calculate. Okay, so 2 to the 1023, and then you have everything, all the mantissa bits are 1, so you're going to have 2 to the 1023 plus 2 to the 1022 plus 2 to the 1021 plus 2 to the 1020, and so on and so forth. And if you keep adding this, it will add up to double X max. Okay, if you try to break it by doing 2 to the 1020 again, this will tell me it's infinity. Okay, but I can add 19 and I won't break it. Okay, and I'll get something closer and closer to the machine double X max. Okay, I would have to carry this out for 52 of these things. I guess I can do 1023 to, what's 23 minus 50? Is it 975? I don't know, what is this length? Okay, I need 3 more, 972. Okay, so then I can do sum of 2 raised to this thing, and that will be dot machine double X max. Is that equal to dot machine, what's going on? Dot machine $ double dot X max. Something's not quite right. Let's see. Okay, 1023 to 971. Okay, so that will equal dot machine double X max. Okay, there's a consequence. Something weird happens. Okay, sorry. Just stick with me one more extra minute here. Okay, what will happen if I do this? Okay, if I say x is 0 and then I create while true, I create an infinite loop where I say x is x plus 1, okay? And I just let this run. And say I have a fast computer and I come back a year later, okay? I've been letting the computer add 1 to itself and it's been counting for a long time. Okay, what number will x be? What number will x be?
The machine max.
Okay, do you think it'll be the machine max? Okay, it will not be the machine max, okay? So what happens, okay, is that, so if I say x is this, I can do x is this, and I can do x plus 1, and I can count, okay? X plus 2, and so on and so forth, okay? But what happens, okay, is once I reach let me say x is this, okay? So x is this. If I try to do x plus 1, look what happens. It returns the same number. So x is 900, ends in 992. And if I say x plus 1, it ends in 992 again, okay? I get stuck here. What has happened? Okay, what has happened is, remember, as we go on, as our mantissa bits fill out, our increment size doubles, okay? So this is the point where my increment size is 1, okay? And I can keep counting by 1, but then I reach a point where my increment jumps up to 2, okay? And so adding 1 fails, okay? Adding 1 fails, and it can't distinguish between 992 and 993. It can, the increment size is now 2, so I can add 2, and it will recognize this as being different. It'll go from 992 to 994. But if I try to add 1, it can't do it because it has no way to distinguish. It's run out of digits to keep track of things. And so the increment size is now 2, so now we have to take step sizes by 2. And if I take step sizes by 2, then it will reach a point where it no longer recognizes step sizes of 2 because the step size jumps up to 4. Okay? So what happens is when you get to really big numbers, your step size is now like 1024, and you're like trying to distinguish between, you know, some number and like 300 less, but it's not able to do it because it doesn't have enough digits to keep track of it, right? And so, so this is like an interesting consequence that we often don't think about. We often expect behaviors like real numbers, but they're not real numbers. They are distinct locations on the number line there. Okay, we will end there. Thanks for sticking around. Have a happy Valentine's Day. Enjoy your extra day in the weekend, and we'll see you guys on Wednesday.